So we will start with the problem statement that we are going to talk about for the next 10 minutes is speech recognition system. Basically, it takes in any voice input and then convert that into a string of text. And now let's fix it as a language that English. And for sake of discussion, we will be. So there are several use cases that you could find for this. The type of recognition, it could be something where you are reading out a book or reading out a conversation, or one where you are having a conversation and one where we are trying to issue some kind of a command and get a program to do something for you, more like our speech assistant of the other day. So for the sake of this we will talk about a speech assistant that works on the command control and sort of the mode. So going to the next slide, we'll see the ideal state that we want to go is in long term is speech recognition is really one where you are able to see whatever you are seeing in as a raw input, a black box that's how you know we are in a neural network. You are able to get out of the plain text or whatever you are saying, which let's say you just said hello, and the magical neural network that transcribe it as h hello, HALLO. That's a sort of end state of voice recognition system that we are they are not there yet. There are plenty of these part that are done in a combination of network of deep learning that nowadays are replacing several of these individual pieces. And what I want to leave you with the stock is which of those pieces have been replaced and what left to do, and how does scheme complicates this. So let's go to the slide. uh, and let me start by telling you how a traditional speech recognition pipeline works. And so when you are speaking, let's say you are saying hello, the first thing it do is to convert this feature representation like we do in all ML problem. Is we have a decoder that is really the three piece to it. Now one of the pronunciation models, so that in the brilliant framework that love I just talked about, and you think about is what is the probability of having a particular utterance when you mean to convey a certain string of word. That is broken down into three component, and the pronunciation model, what are the different ways of pronounce a word, at the acoustic model, what are the different phonemes and a acoustic signal is associated with an language model, or really how often do you expect a certain word to come up, and what is the probability that you are curing a certain word that is common in a language. And the advantage of these traditional pipeline is that these three things can be independently updated. So if you have a new pronunciation for a word, let's say you want to extend an English voice recognition system to understand Indian accent, then it is just updating your library and pronunciation model. Similarly, if you have a new type of acoustic characteristics, you have different mics devices and different acoustics, then you are updating a different model. So this has to its pros and cons, and many of you might know when you are able to update simultaneously, or you also lose a little bit of debug ability. So whenever you encounter a new situation in which your pipeline throws really bad result, it's very hard to tell which of these models are the problem, where should you really be focusing on to make an improvement, and becomes a very expensive and expensive to tire or do all these three things and try a process a speech sample. Speech is a different way so that you get more accurate answer. So now I will take you in a deep learning picture, and the same thing on the next slide. You will what you see is, so let's try to formulate the deep learning wave. So our goal is that we want to start a speed signal shown in the diagram as x, which is input vector, and you want to go to a word y, which is in this case hello, and that is a transparent, that is the voice transcript of someone saying hello. So one of the things that speech recognition system start, which is a spectrogram, which is basically how much energy each of the frequency in your wave contained. So a representation of that is what one calls a spectrogram, and you start from that, and then you try to replace the acoustic model, which is looking at what are the possible for me means, and what are the possible word part that could be the user intent to convey. Given that whatever they have said, so replacing that traditional speech recognition pipeline has led to deep learning and led to more than 20 increase in accuracy. So plenty of what you are able to see the likes of Alexa, Google Assistant do today are really because of the shifting of the conventional model to an acoustic pipeline to more deep learning based model, which really works on recurrent neural network. I won't be going in depth for those, but sort of leave you with the feeling what they are doing, and the reason the problem formulation is hard is that different people say hello in a different way. So you are no longer in a, like trying to do language learning from here. Then you have a certain way which a word are represented. That is a it's a fixed length for hello. The word in the hello are in fixed length. People might say hello in a different word. Somebody might say hello. Somebody might say hello, and they are my characteristic. Their way of stressing a symbol, and their accent is really led to different length and your input factors. So the first problem really in deep learning is how do you transform this so that you have a fixed length vector for a given word. When you go to the next slide, we will see the sort of three steps to do this. The first thing is we use a fixed grammar, which will let us say we are going to stick to phonemes and stick with graphemes let for the purpose of this talk. Just talk about the phonemes. These are the basically pronunciation unit of a word, and what we then do is map the input of the and output neuron that encodes these phonemes, and we try to make a map between the phonemes, which is called data on the slide to a word, and then what we I maximize the likelihood of finding a particular word under this model. So sort of odd of max of finding the word, given that increase your maximum probability of seeing what utterance the user gave you. So in this particular formulation is called as connection of temporary classification. What you are essentially trying to do is find the most likely word given in the utterance. So in this next slide, uh, we will see the sum of the assumptions, the sort of help formulate and help get ahead. So obviously, if I said you will know the likelihood of seeing and different forms of the curves, right? So so without worrying about that, and without treating each of these trends and phenomena that are independent from each other, we get a formulation in which you are trying to do is look at how possible is the word hello from, and set the phonemes you land and then represented it on the left side. And there are a lot of standard algos to this. If you are trying to build your own speech recognition system, you can look up what is called CPC, and then there is a gradient method to solve the CDC, and which comes out with more likely set of phonemes given a word, and that what you will get out of playing with the CTC based RNN moving uh, so given that we will go to the next slide, and the last part of this slide. Then the way we do this is in production today is really simple and language model, and that is you talk about the trigram or the bigram, and then you are basically saying that what is the probability of word occurring, the user utterance. Just let forget everything. about the user and how. Now let's just look at the facts of the language is English. And so we are kind of learning from a what is the likelihood of somebody saying hello, and there are other things. What is the likelihood of somebody starting with hello? That's pretty high. Similarly, there are ways to adapt this to a particular user. So the more that model get adapted to the particular user context, the more likely you are able to predict the things. Because what they are going to say next more accurately, so that the sort of intuitive of thinking about it. The problem with this is a particular problem called Chisholm problem, and which really is hard to using this context. It is going to be very hard to figure out what the word is. You are likely going to be doing some errors. So plenty of you might have seen this happen, that a voice assistant, that some kind of a error pops out. A lot of this problem one of these problem with language at the scale is really hard to tell with specific utterance. So what is the commonly known word, and it's very difficult to use language model to sort of guess word. The last piece that I want to leave you is to complicate is the scale. The first thing that complicate it is the scale of the different user have different kind of acoustic, and they are exposed to different kind of noises. The way deep learning practitioner try to solve for these really take synthesized noise, add to their voice input, try and retain the network, and see what we land with, and keep trying to add more noisy variant of the same sort of utterance and the other things in a huge computation. As you can imagine, if you about even thousands of user using this voice assistant, and you are gathering enough data from them in 2 hours a day. You end up with a huge number of utterance, and it is computationally really complex. Today, in a state of art paper, you use more than 20 GPUs of process, GPUs of process, about a million hour of speech, and that's the scale at which this compute happens. It's about 10-20 flops, which is really huge. It takes about 30 days, Titan core. So there's a new problem or scale of how simply this compute. How can you get more of the GPUs? How can you really compute faster? And there are techniques in mini batching. There are trying to align utterance of similar length together and send one batch, and not too much of variance in the length and of the utterance in a batch. So you are optimally using the compute. Many problems